I think we're online. So, couple housekeeping points. Homework due Friday. For those of you who were watching on the internet before, did you see my discussion about the answers? I was trying to be very clear.
We were commenting during the lecture, but I don't think anybody noticed.
Yeah. Oh, I'm sorry. Yeah, I did.
Just to each other.
Oh, okay. Yeah. Oh, that's good.
It was more just like you guys were probably all missing our normal little like, so we just were trying to add that in.
Oh, that's good. Yeah, and if I not having the multiple screens here, I feel like I should. I don't know. I guess those comments are public, right? So everybody can see them. So, hopefully.
We stopped when we realized no one was responding.
Yeah. So I don't know. And this is me being. I love technology, but I just haven't studied this one enough. It's like, is it working? Okay, cool. I'm just going to go with it. So, but yeah, I need to look into that more. I think when I teach multivariate in the spring, if I have the time, it's a big if, but I want to commit to it. I want to do a flipped classroom because that's the one where we have my TA is right here. That's the one where we have sort of your introduction to R. So if I could teach lecture just online, but then have people, that's like the homework. The key is getting people to do that. Otherwise, people aren't going to mess it. Then we'd have like 3 hours of R interaction more. So I'm hoping that would be. Would anybody have any thoughts about just?
Is that the same class that Billy taught?
Yeah. Yeah, but mine's a lot.
You could say better.
No, I don't know about better. I'm not going there. I don't know how Billy taught. I gave him my materials, but I think he sort of stopped after a while. The online homework system. No, you were in it.
No, that's
okay. The online homework system he didn't want to use, and that makes it so that it can be hard at times because you're learning R while you're learning material, and like the first homework is notoriously bad. So I'm trying to find a way to soften the blow a little bit, but also try to maintain some type of fidelity to instruction. So what do you think? Does a flipped classroom sound like a good?
I would have loved that when I was trying to learn R.
Okay.
Is it flipped or will be blended?
I guess flipped or blended. I want to make the lecture part like more of an active learning environment. So you have a laptop and there's an example or there's something you have to work through in R, and that way you can have a chance to interact with me. I haven't talked to the TA yet, Ji-Hung, about this, but interact with the two of us. I would sort of loosely introduce the example, but then you could pair up, you could do whatever else, and it would be bits.
Collect data on it.
Yeah, I should. It'd be interesting. But does that sound? What do you think? Pluses, I mean, just feedback. Anybody? I'm just throwing it out here.
Yeah, listening to somebody like showing R is not really helpful.
Yeah.
Like, it looks easy, but when it's my turn to do it, like
gosh,
it's not easy. Like
you have all these little nuanced problems that you have to talk to somebody about. Yeah, I mean, I think it sounds like a good idea, and I would definitely appreciate the chance to do like more work through things with you. At the same time, I definitely learn a lot more of the content when the lecture is in person as opposed to online.
Fair enough. So maybe there's a way to, if I could have, we're going to break up lecture into a little more digestible chunks, so it wouldn't be like an hour. It would be more, different topics lumped together. But if there's a way I could have maybe even the comment section, when you get to a certain part, put the timestamp and put a question down. And so maybe as you're doing that, would that be something? So we could talk. I mean, that ultimately, maybe the first part of lecture could be just addressing questions, or maybe we do a little bit of R, and then just to kind of get the focus again, because sometimes that solves questions by doing things. Does that sound? No.
I wonder if during maybe you could integrate in class time, but I was thinking for office hours to have like a Zoom room for office hours.
Yeah.
Where somebody could just come in, share their screen, and show like their R.
That's a good way of thinking about it. Yeah.
Somebody else could just come in, see what's happening, and even if they don't have a question, just like observe, and then you could record it on Zoom and archive it too. So
that's a good thought. That's a good thought. That is a good thought.
Label those archive records with like what the specific issues were that you were going over.
Oh boy, yeah, that's going to be it's harder to label. That's the hard part with the digital media. Like, how do you? I don't have a lot of time to splice after I'm done. So
But not
Like homework
slice,
one
like
related.
say, like
Mhm.
homework one, yeah.
Okay, I
Oh,
can do
yeah,
that.
like,
I
or
can do that.
address.
Yeah, the other thing I have, the issue with the archive, I think I'd have to get the permission of the person who's coming into the room, you know, privacy-wise.
Just get everybody's like agreement at the beginning of the semester.
True, and if people, you know, I think they'd have to opt out or something like that. But we could make that work. Yeah, I think that would be, because ultimately I think that's the big fear of a lot of people. If I make it a video recording, a lot of people don't want to ask the question because they're afraid they'll look foolish among their peers. Which to me, I think I've been in your shoes before. I remember being laughed at for questions I've asked. I hate that. So
During the Billy's class, Jihan.
oh, the TA.
Yeah, he actually had a couple of times for R to go through R.
Cool. Yeah, and that's what we were.
And that was helpful too.
Yeah, I think that's what we talked about a little bit. But I was thinking more of, I'd like to have the class experience be more working through it. But also, I do need time for questions. So I've got to find a way to do that. Find a way to parse the two. Like you said, office hours, I think the Zoom room, again, I'm sort of in, I think that's a great idea. The question is where's the FERPA applied to questions that students have?
Yeah.
And so, yeah, I don't want to, I don't want to make people feel pressure about coming to office hours because they might be on a camera. But having multiple chances for people to bring their laptops, that's what I sort of do anyway. But also, if I could find a way for people who could submit, that's it. Submit questions, like put a timestamp and ask a question. Say, you know, in this section I don't know this or something like those lines. Maybe that. And then they could submit that to me ahead of class. And we have 1 3-hour class meeting a week. So we then sort of start with the list of questions. But I could remove the names so nobody knows who's asking them. Something like that. Would that?
That's a good idea too.
So so they would go through it and you would just get the questions. Nobody else would see the person's questions.
Right, or I could bring the list of questions, but just remove the names, so nobody knows who's asking which question. So it's sort of effectively anonymous. I mean, it's not anonymous to me, but it's anonymous to the group. I do feel like, particularly in the 905 class, the way I teach it, there's a lot of peer pressure to not look stupid for whatever reason, and I don't. And the thing is, you don't look stupid to me when you're asking the question, but I can understand how that pressure might be. Well, I'm the only one who has this question, when really, this group has been great because questions seem to come all the time, and I love that. But that doesn't, I can't quite get that same rapport. Maybe it's the classroom, maybe it's I don't know what, but it's harder to have that rapport with every group. So.
Is it the one? Are you teaching it the same where Billy taught it downstairs?
Yeah, unfortunately.
That's a terrible thing for a class.
It really is, and that's where I was thinking. Like the other thing, if I flip it, where the lecturer is really online already, but then that's just a place where we have group interaction with.
Doesn't really facilitate group.
Yeah.
True.
Either. It's a lecture.
I almost think it's worth a class not like even if that means okay you can't be in JRP. That was so bad.
It was terrible, huh?
Too. Yeah.
Yeah, well, we were somehow put in the Military Sciences building. I don't know if you know where that is. It's between Anschutz and Summerfield, on kind of going down the hill over by Mallet. And...
That's where Peter is teaching regression.
Oh, is that where she is now? How is that going?
I don't know. I just have a couple friends who are taking the class there.
Yeah, that's right. You would be in it. Yeah.
Yeah.
I think it's in Summerfield.
Oh, Summerfield instead, huh?
Also,
Well, I'll look into that and see what other rooms are available. So that's good. Anyway, thanks for feedback. I just wanted to.
There's lots of feedback.
I like it. It's important. I'm trying. The thing is, I don't ever want to get stagnant with what I do. So.
That's not yet.
No, I'm like I love change. Like change is like I thrive on it. So it's fun, but that also means I'm sort of experimental with class, and that sometimes doesn't go well. So, but having most of you haven't taken Billy's just last spring, it seems like you're a good audience to ask questions about. So.
And I was only teasing about better just because I know you would say you go back.
Oh yeah, we go back and forth. I'll tell him
I
that.
didn't mean that as a really intense statement.
Billy, you hear that? No, I'm just kidding. I didn't say it on here at least. I'm not in trouble. No, Billy and I go back and forth. Yeah. Yeah, never mind. I'll stop saying it. So, do you remember where we left off? Invariance testing. Your first test of it was like SEM, almost there. Like at the end of invariance testing, you could look for group differences, which is like having a regression model predicting one of the factors with an external variable. But the rationale we need to do is make sure that the group differences are not due to differences in parameters of the items. And that's where this invariance testing comes about, or differential item functioning testing. So instead of we stopped here on the metric invariant slide. I know this because PowerPoint conveniently just pulled it up for me. But we're going to go and look at the examples now. And I'm just going to stay with, rather than draw on the iPad, I'm going to stay here with the screen. And I'm going to grab example 7A, which I just re-uploaded today because typos and whatnot. What you're going to find with this is that there's a lot of, there's a lot of syntax that goes with this, but it's all models that you're fairly used to, right? You're fairly used to CFA. We're going to start in the CFA world, and we'll expand it from there. So the example I want to show you, can everybody see that? Okay, do you need it larger? Larger. Is that better? Okay, here we go. So what this is using that same data, actually this is not the same data. This is a data set with 345 people evaluating major depression criteria across men and women. And there are 9 different items. And evidently this is some type of rating scale by clinicians. So this might be some type of form of an interview, like data that's collected in an interview format. I'm not sure exactly, but here the items are things like a person has a depressed mood or loss of interest in usual activities and so on and so forth. And they're on a scale from 0, which indicates none is present, to 8, which is very severely disturbing or disabling. So, for instance, in depressed mood, if you're being evaluated by a clinician, you're probably in there because you're not a 0, right? So, there's, or this is maybe you don't feel depressed, but there's some other type of issue that's arised, and this is sort of related to it. I am not a clinician. I am not equipped to go and say that. And I have great respect for those in the clinical fields in any of the accredited programs, particularly school psych and counseling psych. Where's Michael? I thought I saw him. There he is back there. Did I miss any counseling psychologists in here? All right. Way to go, guys. It's a tough field to be in. But let's start with the idea how we worked this before. Remember, when we start in this analysis, we start with something called the configural model, effectively. Right? We're supposed to say step 0 was, are the covariance matrices the same between the two groups? We're not going to look into that. Step 0.5 or step 0.5 was like, okay, if the covariance matrices are different, do the two groups have the same factor structure? Well, we're not going to test a different factor structure in each group. We're going to say it's unidimensional. There's one depression factor. Right here, we're going to call it depress. Person who is higher on that factor will probably have elevated scores on each of these, or elevated ratings on each of these by a clinician. So we're just going to start with the idea that each group, there's one factor for each. What we're going to try to do is see whether or not the items are invariant across groups. One thing I wanted to note with LaVon is you'll see here when I read in the data, I have a bunch of items, and the original data comes with a dummy-coded variable right here. Oops. That I've labeled sex, person's sex, 0 and 1. But I found that's because, well, in M+ you can do it in different ways too. But having LaVon is nice because you can actually provide a character-based label to it. So one of the things I hate looking at when I'm looking at output is group 0 and group 1. Well, which one's which, right? So I recode the variable so that it's just the actual character itself. I actually create a new variable called sex. Actually, no, it is sex. It's the same variable. Basically, I'm turning every 0 to female and every 1 to male. So you should see in the output, you'll be able to see a section for females and a section for males for each group. So moving forward, the first model is the configural model, and this is where I'm breaking down the syntax a little bit differently this time. In the syntax itself, I've tried to divide it with these comments in code and the equal sign. So this is sort of a marker as to what's going on. And because this is a CFA model, we have factor loadings, we have item intercepts, we have residual variances. Right? So each item potentially has those 3 parameters. We also have a factor mean, a factor variance we have to worry about. And now, because there's 2 groups, we're going to start with the model. The configural invariance model basically says, let's allow the scale to be completely different in each group. The parameters to be completely different in each group. So we're starting with the idea that everything is different and then sort of winnowing our way down to try to figure out what's the same. And the rationale, again, for that is that when everything is different, that's sort of the best fitting model there is out there. Right? So we're going to start with the idea that everything fits as well as it can and then sort of lock in what we can. And the reason for that is with best fitting models, we know that we're not going to have bias in our decisions that we make. Whereas if we start with the other way around, everything is the same across groups and we try to free things, that is sort of essentially that may be the worst fitting model that we're starting with. Ultimately, it may fit equal to the best fitting, but if it doesn't, using it for decisions is problematic. So let's go through the syntax. The factor loadings themselves start with, again, the name of the factor, which I'm calling depress, the equal tilde. And then things start to get a little weird. I've went ahead because every parameter in this analysis is going to be something that we need to constrain across groups. The way LaVon uses constraints is through the idea of the labels. Remember labels before? We used labels to put equality constraints across items and so forth. Particularly when we were doing the tau equivalent model, seeing if the factor loadings were the same, we put the same label times each of the items. When you have a multiple group model, those labels are now enclosed in this syntax that starts with a C, and then the open parenthesis and closed parenthesis. And then for each group, there's a label separated by a comma. Right? So the C syntax is meant to mimic R's C function, which sort of glues each of these strings together. But it's not entirely the same, because if this were truly a C function that we'd see in R, it wouldn't know what to do with this, because those 2 objects within it should be in quotes right here. Right? So LaVon is sort of stripped off the quote. Yeah, that's right. Otherwise, it thinks of them as objects that they can't find itself.
So when we run it, do we add quotes in, you're saying?
No, don't add the quotes. In LaVon syntax, you have to think it's R-ish, but it's not exactly R. If you were typing this in R, it wouldn't be an actual command. Sorry, if you were typing it directly into R and not into this character string that LaVon syntax is housed in.
So what's interesting is that how LaVon will recognize that F will stand for female and M will stand for.
We have to know, and so what happens is it alphanumerically codes the group, so that when you tell it the group variable, which comes in in the LaVon syntax when you run the model, it figures out alphanumerically what the categories are, and then the first entry into this C function in your code is the one for the first group. And so because female starts in the alphabet before male, we know female should be the first group, and that's where I labeled it F and M. Ultimately, though, that's something you sort of have to, I learned that through trial and error. And there may be, particularly in the numeric variable, like if you have a 0, 1 number or something like that, you have to sort of be very attuned to that. Yeah, so you see each item now, because this is a different, so what this is effectively doing is applying the first label to item 1 for the first group, and the second label to item 1 for the second group. And because this is L1F in the first spot, and this is L1M in the second spot, the labels are different, so the parameters will be estimated separately. Right? When we go to constrain to see if the factor loadings are equal, can you imagine what happens? If we make the same label, right, if this is the same value in each spot, one estimate, that's right. When it's the same label, that means the parameter estimates are the same. You got it. Where are you going for? Did I hear you like yes? Is that what you said or no?
Maybe in my head, and then it just came out. I don't know.
Okay, that's cool. That's cool because it's good to be.
It's kind of analysis of variance here, like for each single item, analysis of variance.
Yeah, what we've got here for each item is exactly that. It's actually an analysis of covariance with an interaction term. So this is sort of what's happening in the code. So you see, I have all 9 items, and before each, there's this crazy looking label thing. That takes a long time to write. But I do that for every parameter in the model. That's the other thing that's the problem. Like LaVon has tried to shorten this syntax in other ways, where they have like little catches to try to automate parts of it, and I found that none of those catches ever work the way I want them to. Same thing in M+. They try to automate the steps you'd have to take. The problem is when you run into a step, if we're going to check that the factor loadings are equal, which is called metric invariance, we constrain all the factor loadings to be equal, and we do a likelihood ratio test between our model and the configural model, the metric model and the configural model. And if that fails, what do? You've got to go back to your data and figure out which ones aren't equal. And to automate that process, because the decisions themselves may be somewhat subjective, to say the least, it's very difficult to automate. So it's laborious syntax. That's what I got to get to you. Takes a while. Not only that, the way I'm teaching you is we're going to use the LaVon function. The LaVon function works a little bit differently than the SEM or CFA function that I taught you before. I sort of showed you LaVon at the very beginning. What you have to do in LaVon is specify all the model parameters. Right? So that means we need all the item, factor loadings, intercepts, residual variances, residual covariance if it's there, and then factor variance and mean. But we'll need those anyway for different parts of this analysis. So that's why I'm building it in at first. So you build this big syntax file at first, each with a different label. That's the thing that takes the most amount of time. You can copy and paste that subsequently when you start doing the different analyses after that. How are we doing? Okay. So those are the factor loadings. Item intercepts work the same. Again, it's item tilde. The previous syntax was item tilde 1 was the intercept. But now what we're doing is item tilde, and again, that same clunky code for the label for each, star 1. Right? And so you see this all the items. Residual variance work the same way. Before, bless you, the previous syntax was item 1 double tilde item 1. But now it's item 1 double tilde label times item 1. Residual covariance. It was item 1 double tilde the other item. There's actually residual covariance in this model just to show you how it works. You know my preference. I don't like the residual covariances there. This is like depression and stuff, right? That's what we're measuring. But this is more to show methodologically how you treat it in the steps in the analysis. Item 1 double tilde item 2 with the label in front of it. When we get to factor variance, this is the one thing that's different. Before the factor variance, again, we treated it just like an item variance, where it'd be the name of the factor double tilde the name of the factor. But because what we want to do in our first configural analysis is to run these 2 separate analyses where we're estimating all the factor loadings, and the reason for that is we want to test all the factor loadings, we have to identify the factor in each group, the scale of the factor. We have to sort of set the scale. So we're going to set the scale by putting an actual number in that parenthesis now. When you put a number in that parenthesis, that sets the parameter to that number. It doesn't estimate it, and it sets it to that for the respective group where the number appears in the sequence. Right? So the first number represents the value I'm setting for the factor mean in the first group.
Why did you set it as 1?
At 1, it's the standardized factor identification. So remember when we started talking about CFA, same thing held with IRT. We have to figure out we have to somehow set the scale of the latent variable. When we set it to 1, that's sort of we can estimate all the factor loadings, and so that's where I set it there. It'd be equivalent if I set it to 100, but 1 is sort of a convention that we use when we standardize it. Same thing over here, 1 for each. Yeah.
Just like I know this like an example like before, but is it exchangeable? Like the location of the C parentheses would be multiplied by the factor itself or by 1. Like, can we put like the 1 then the sign for multiplication in C?
I don't know. I haven't tried it. Just followed their example online. You can try it and find out. If it doesn't blow up, maybe. But I haven't tried it. And honestly, I've run so many of these darn models in the last like week. I'm so frustrated with it. I don't even want to try right now. Right. Sorry, the whole invariance process is a very aggravating one, but it's necessary, I feel like. So also, that's the factor variance. The next thing we need to do is set the factor mean. We're going to set the factor mean to 0 for that standardized factor. And we're going to set it to 0 in both groups. And this is where I do depress single tilde. And before, you would just see the number 0 afterwards, indicating to set the factor to 0. But here it's a weird syntax of the label setting it to 0 times 0, indicating it's the mean for that factor, which is sort of an odd thing. How we doing? Okay, once we do all that, once we have everything specified, we can create our LaVon, or run the LaVon model itself. This is, again, the LaVon function. It works very similar to what you saw in CFA. In fact, the arguments we pass to it, configural syntax, the thing we just created, the name of the data, we want estimator to be MLR again, and we want to mimic M plus again. Those are the things that are always standard. The new thing that shows up is we're going to add group equals, and in quotes, we're going to put the name of the variable that represents our grouping variable in the analysis. So in this case, I named it sex. Then you run the analysis, you run the model, and sure enough, to summarize, to show the summary statement, you get the configural, you put the model object, the thing that contains all the information about the analysis, just run into the summary function. And again, like we've done through every model in this class, add fit measures, add R-square, add standardized. So shall we run this? Let's see what happens. It takes a little bit of time, it converges, and now let's take a look at the output. It tells us the number of observations per group, 375 each. There's one piece of missing data in each group. And here, this gives us remember this, in the original version of CFA, this first test statistic was the test of our model versus the saturated model. And what this is telling us is that even our configural model does not exactly fit the saturated model, but that's going to be the case in most of what we do. Saturated being this is the test of our model versus like the unrestricted covariance in each group. Right. So if we were just to go and fit the model that had all the parameters we could possibly throw in there, that would be the saturated model, and this test would compare them. The next group thing you see is now a new piece of output, the chi-square for each group. What you'll see is that these two numbers sum up to give you the total up here. That's all that comes from. It's sort of like, where's the contribution from each? I never look at that. I really don't. It doesn't tell me a whole lot. In this case, I guess it tells me a little bit in that the items are on the same scale. We have the same number of people in each group. So effectively, it's like saying the model fit for the female group is a little bit worse than the model fit for the male group, but that's not exactly the case. It's sort of an odd thing to say. So see that and take it with a grain of salt. The other thing is the numbers that appear in this section are heavily dependent on the number of people in each group. So you have a widely discrepant sample size for each group. If it was 1,000 in one group and 100 in another, the chi-square for the 1,000 is going to be larger. That doesn't really tell us much. So going down again, the model test for baseline model. This is the comparison of the model that had 0 covariances in it with the saturated model, which is the model with all the covariances. That also doesn't tell us a whole lot. But then we get everything else that looks similar. The CFI, the TLI, right? We want those to be high. These are pretty good. We get our log likelihoods. We get our number of free parameters. We get our information criteria. And then over here we get our RMSCA. And you'll note all of these are not separated by group, which is the only way we can do it. And our SMRMR, standardized root mean squared residual. Everybody okay? That should be a little bit familiar.
Just
yeah.
For the first statistic, like the minimum function statistics, the comparison between this model and the saturated model.
Yes.
Out of curiosity, if the two are not like this model and the saturated model is perfectly like mirror each other, we would have non-significant.
That's right. That's right. Which rarely happens, although it's great when it does.
This is
Yeah.
slightly tangential, but you mentioned like having different numbers for your groups. So what if it was something like where one group you have like a 5-to-1 ratio versus the other because the other group is like so, I guess, unique and hard to collect data from? Is this controlled for?
Yeah, it tries to control for it. It tries to basically these is like doing two separate analyses altogether and putting them back together. So this in this analysis itself, the configural model, that's exactly the case because they're just independent altogether. So yeah, I mean, now the necessary things that show up with small sample sizes, the ratio of the sample size to the number of parameters, you know, when there's a lot of parameters per unit of sample size, it's sometimes harder to get the model converged. That will still be the case, particularly in the configural model because it's so separate. But here it sort of waits for it. I mean, it adjusts accordingly. The other thing I wanted to note, let's take a look here at the output. Finally, when we get down to the actual item parameters, now you'll see the labels that we applied. Right, so this is how I check, right, the guess and check to make sure that the group is right. The first group, this is group 1 output. This is my actual character that describes it, female, and this is where I check that my label is appropriate. F F F F F. You'll see that. These are the factor loadings for the females, and these are the the standardized factor loadings, everything that you'd see before. And so everything in this output is what you'd seen in CFA before, but just applied to the females group. Right? So then you see the items, the factor loadings, you see the residual covariance between item 1 and item 2. You see the item intercepts, again with the labels. You'll note the factor mean is set to 0. That's a good thing to just double check on. You see the variances for each item. You see the factor mean is set, the factor variance is set to 1, good to check. You also see the R-squared. Right, so it's entirely like having this analysis in CFA just for the group female. And again, that same output now gets replicated for each group. So in our case, we have 2 groups. Second group is male. And now you can see the factor loadings, right? You can compare and contrast. Like the first factor loading for the first group was 1.251. The first factor loading for the second group for males, 1.024. Are those significantly different is the question. I don't know. We're going to have to find out in the next step. But you'll see the numbers will change. You know, the thing to note is they're changing, but these scales are, it's like, again, it's comparing apples to oranges right now. There's nothing that locks these two things together. It's like having, like we mentioned before, just because the mean and variance are the same for 2 variables doesn't mean the 2 variables are the same thing. Right? And I talked about height and weight, right? If I take, you know, if I have a bunch of data and I make a z-score out of height and I look at a z-score out of weight, it's still 2 different constructs, 2 different things altogether that they're representing, right? And so this is where we're at right now. Even though it's called depression, it may be depression 1 and depression 2, or it may be a different type of depression in each group. That's what we're talking about. So because of that, it's hard to directly compare the output, mainly because these things are on different scale. There's nothing anchoring the metric together right now. So even though the factor loadings look a little bit different, that's a good indicator there may be a problem, but it's not the only indicator. There may be other ways that they're different for, right?
So if we look to the standardized column,
yes,
which means they are in the same metric, if not mistaken.
But they're all in the same metric anyway, for the most part. The thing is, even if you have a standardized variable, they may not be the same construct, right? So think of it this way: like if you have your height in like centimeters and your weight in like kilograms, right? If you take a look, if you make a z-score out of both of those, right, for each, they have the same mean, they have the same variance, but they mean completely separate things, right? And so that's where we're at here. Yeah. It's really tempting to say, oh, it's the same mean, the same variance, and oh yeah, it's depression, right? But it's not exactly depression, right? It could be something that's different. Yeah, sure.
I'm looking at the one online, and it's not the same numbers.
Oh Lord, I don't know why.
But Miami has it printed.
Yes,
that's right.
What is the matter? Oh my goodness. Yeah, I don't know what the deal is.
It looks really similar. That helps.
These are all the same files I got the things from online from. Let me see. The online example now is from 11/27. You may have to go and hit the refresh button on your browser, maybe? I don't know. Oh, you did.
Reopened it again.
That's really frustrating. Let me see. This is the... Oh, the configural invariance model doesn't even have the actual output for it. Oh.
Right.
Okay, so yeah, we're in configural right now. We haven't gotten to the... So somehow I deleted off the output for that, which is really weird because it's in here in my slides. So.
Okay.
Yeah.
That's weird.
Well,
That's...
the numbers might be different though. I was looking at it in my R script, not your numbers. You're on group 2.
Yeah, I'm on group 2, but I'm on the configural, not the metric. So if the metric doesn't have it...
I mean, I see there's no output.
Oh,
after
yeah,
it.
no, there's no output.
Yeah, so you're looking at the metric one right now. There's no output. I don't know how that happened because I got it from this file. Anyway, I'll have to... Sorry. I'm just a little frustrated with it. Need to contain my...
From
Yeah,
a
but
couple
he
days
has
ago.
it.
Couple days ago. So,
Yes. But do you get the concept though?
Yeah.
Different model, interpreted the same. There's not a whole lot we can say. This is our baseline model, right? Let's go and do metric invariance.
Can I ask
Please.
one question? So we're doing CFA, right?
Yes.
But then the in front of it is a LaVon. The
That's right. The LaVon, the way we're going to access CFA is the function is going to be called LaVon. And that's the most generic version. So LaVon is a package. I taught you CFA before because it allows you to shorten your syntax.
Okay.
But for this analysis, we need long syntax. And because of that, when we do CFA with this analysis, the shortcuts it takes will sometimes, well, I don't know exactly, but it may overwrite the syntax you've put in to lock in features we don't want to have there, right?
Okay.
So we stay with LaVon. The penalty for that is all syntax needs to be long. Well, it turns out we're going to need the long syntax anyway.
Okay, so as we have more practice, we know which one to use.
That's right, yeah. I mean,
Okay.
if you're doing anything but a multiple group model, the CFA version or the SEM version is usually sufficient. It's when you have to start getting into the weeds of each of the parameters, it's when I usually switch to LaVon.
Okay, that's more helpful to understand which one to use.
Yeah, the other ones, everything, like when the way it works is everything is built off of LaVon itself.
Mhm.
So what CFA does is it takes your syntax and it adds in a bunch of other assumptions and then submits it to LaVon. Right, so it's trying to shorten how hard it is to run the analysis for you, which is a good thing for most of the analyses. We don't need the full stuff. But the problem is with this, it's the interaction of what happens when you specify syntax, but then it either there's a disconnect between it and the CFA version of it. And actually, and I'll tell you one step, not to confuse anymore, but the bigger issue is in CFA we had to say, when we wanted the standardized factor, we had to do std.lv equals true.
Yes.
We have a standardized factor in this model, but we're pretty soon going to not be standardized, and that's where the big discrepancy is, right? So when we do std.lv equals false, it goes and estimates each of these, and in my initial configuration with it, either I was doing something wrong, probably was doing something wrong, and I couldn't get it to stop. It was like overwriting it. So that's where I'm going with LaVon. So. Okay, so we do the metric model now. So we see if the factor loadings are all set to be equal across groups. All right, so to do that, we take the label from the very first set where the factor loadings are, and in that C function that shows up where the contains the labels for each group, we just make the label look the same on either side of the comma. Right. By the way, if you had 3 groups, there'd be a third spot, right? Within the C, it's as many groups as you have in your analysis, right? So you have 3 labels or 4 labels. And right here, you'll note that I put a star by everything. So there's an interesting thing. If we allowed the labels to be free, to be constrained across each of the analyses, that effectively creates an identification constraint for each group now to where we can actually go forward and estimate the factor variance in one of our groups. And the reason we'd want to do that is because the factor variance has a really close relationship with the factor loading. If you remember the variance covariance matrix we're trying to make our data look like, our model look like from the data, in that there was factor variance and factor loading almost always tied together. So one thing that we do in the metric step that's a little bit different than just fixing all the loadings to be equal. We fix the loadings to be equal, but then we take the factor variance for this for every group except one, and we allow that to be estimated. Right? And the reason for that is it's possible that our factors now are on have different variances. Their factor loadings may be the same, but there'll still be maybe more variability in one group and another in the factor, and we need that to be expressed in this analysis, because if we don't, what it may do is it may say that the factor loadings, once we don't control for the variance, the factor loadings are dependent on variance effectively. We have to be able to allow that to be controlled for in this analysis, and that's where we're estimating it. So the two steps in metric invariance: fix the loadings to be equal, take one of the groups and set the factor variance to 1 like you had in the previous model, but estimate the factor variance. Now, when you do that in LaVon syntax, you put the letters NA. NA means estimate this. Yeah, which is not missing. It's estimate this. Yeah, I know. It's yeah. So
sorry, it's not clear. Like why we need to. I understand that we want to check that the factor loading is equal across the group. But why we need to really estimate one of the variance?
Well, think of it this way: in our previous model, we didn't have the same metric, effectively, right?
Yep.
In this model, we're starting to get on the same metric,
yep.
Right? But the groups may differ in how much they vary on the factor. And if they differ in how much they vary on the factor, it's going to impact the factor loadings themselves, right? So if we don't allow that difference to be expressed in the analysis, we might find that the factor loadings look significantly different, but all that really comes from is the factor variance itself, right? If we change the factor variance, remember what happened when we were playing around with identification before we changed the factor variance? What happens to factor loadings, right? They change size. Now they all change size uniformly because it's the factor variance that's going on with that's governing this. But we need to allow it to be estimated just in case it's different, because that might have parameter implications for us. The nice thing with this analysis is once we've made that constraint across groups that the factor loadings are the same, we can estimate the factor variance in all but one of the groups, because that first group sort of anchors where that variance is at, and that second group will be somewhere around there.
So this is in the case that we are not sure about the metric, like the scale.
That's right.
Support. But if we are 100% sure, like we administer the instrument and we know that the scale is from 0 to 1, and we have like 0, like the mean 0 is, and the standard deviation or the variance is 1. Do we need to estimate?
Yes, yeah, because it's now group specific, and you're never 100% certain about these things. So.
Even though that I set the scale and
did you answer the questions yourself? I'll tell you it this way, right? If I generate simulated data where I know what the true value of the mean of the variance is, I can generate 1 million cases and it's never 0 and 1 exactly.
Yeah.
Right? And so this is what I'm saying. Like, you want to allow as much data-driven evidence to permeate what you're doing, and allowing the variance to be estimated does that. Mayumi, did you have a question?
No.
Did I say something overly offensive there? I feel like.
No.
Okay, good.
I'm sitting here to learn what to do, but it seems like they're really
There's what? There's
just
lots of
many ways to do.
Oh no, there's not really. This is a very strict way, right?
Yes.
Right. So
in general.
In general. Like in general, this is a really good process to follow, because it guarantees if you find differences in a factor, that they're not spurious because they're only differences in the items themselves, right? And so, and because of that, what we're looking at when we constrain the factor loadings to be equal is if we reject this model and we didn't allow the variance to be free, that may just be because the variances are difference between the factor, right? Remember when we changed the factor variance from 1 to 10. Remember what happened to loadings? The decimal place is shifted, right? And that's what's going to happen here. Let's imagine in group 2 the variance is 10, in group 1 the variance is 1, but the factor loadings are all otherwise equal. If we fix that factor variance to 1 in group 2, it's going to want the factor loadings for group 2 to have that decimal place shifted over. And statistically, that's going to be statistically significant, different between the two, even though that's only because the variance is shifted, right? So when we move the variance, all of a sudden we see the loadings move with it. And the reason for that, if you remember the regression coefficient, the factor loading is a regression coefficient. It's predicting how much increase in the score of the item per unit of the factor. But remember, it's per unit of the factor. And so if that unit of the factor is a just sort of substitute standard deviation of the factor, right? If per unit is changing for the two groups, we need to be able to control for that, and that's how we do it. So yeah, I know it's going to sound this is like the most overwhelming set of analyses, by the way, but it's formulaic. So the cookbook is, start with both groups differently, lock in the loadings, but when you lock in the loadings, free the variance, right? And then there'll be another. So that's very. It's going to be very formulaic with that regard. It sounds weird, but the rationale again is because the loadings are tied to the scale of the variance. Does that help some?
Is it like I'm not sure, but I'm trying to connect. Is it related to the identification that we discussed before? Like you have to be careful which variance to estimate, because like when the identification, because we might set the marker.
Right, yeah, if you put it on the wrong item and the item is not related. This is actually not related to that, and I'll tell you why. Because the way that we've identified this is still, this first group's variance is 1. So we've estimated all the factor loadings, right? And this second group we're estimating is variance. That's right. So the factor loadings may or may not, they may all be 0. And that's okay, because we're estimating all of them. We're not fixing them to 1. So, Shada, you had a question.
Yeah. I have 2 questions.
Yeah.
But can you repeat that again? So in the configural model, you are. Can you repeat what you said about the factor loadings? So you're setting them each to have being 2 separate.
Completely separate. That's right. The factor loadings are completely separate. It's like you literally ran 2 separate CFAs, right? And put the results together to get what you found. Does that answer for that's configural. And then when we go to metric means factor loadings. So we lock all the factor loadings to be equal. But in doing so, we estimate the variance for all but one group. And that's because the factor loadings all move in tandem with that variance.
And then, so then in the configural model for the variance, then you fix both of them to be 1, correct?
That's right, because it's this separate analysis for both. In fact, if you tried to estimate it, it may give you numbers, but it's technically not identified. Okay. It's like when we were doing, when we first introduced CFA, if you just looked at a single group analysis, and that's, again, because it's a separate analysis for each, if we wanted to estimate all the factor loadings, we couldn't estimate the factor variance. It's sort of circular. There's too many unknowns in the system of equations to figure out.
Okay, and when you estimate the variance for all but one group in the metric model, then you're setting the factor variance for one group to 1.
That's exactly right.
Okay.
Yeah, and then we have to have that for our identification.
Okay, and then I have a second question.
Yeah, please.
So I've seen in a couple of tables that it'll say configural invariance model, loading invariance model, and intercept invariance model.
Yeah, that's a better way of putting it.
How do you map these on? So configural, I understand, is metric.
Metric is loading.
Metric is loading.
That's right. In fact, I wish we'd all call it loading, because that's ultimately what we're messing with the loading. We're testing the loadings in the metric step.
Okay.
Okay.
And then what is? And then are we going to get to
intercept and scalar comes next?
Okay.
Yep. Yeah. So is that cool?
Yes. Sorry. I just
no problem.
I'm like, there's 5 different ways to do this.
And the thing is, it's just there are still going to be an over-remembering. But basically, what you have to test is each of the parameters for the measurement model in some way, with very few exceptions.
That makes sense.
Slam the door when you go out. Yeah, that's right.
This was a waste of
That's, that's good.
Running joke between us.
Yeah, that's good. That's good. I like it. It's a waste of all of our time. Sometimes it feels like that, doesn't it? And I do this for a living, but no. So does that help? So what we're trying to do? Sorry. Yes.
That happens all the time with Katie.
Oh no. Are we in a good place just to check?
Yeah, and Configural is always called Configural. You'll never see it called anything else.
I've never seen it called anything else.
Okay.
Yeah.
But usually,
I just call it the separate analysis model, right?
Okay.
Because that's what it is. I mean, it's like, separate analyses,
Well, they all are, right?
No, when we start to lock the cross-group constraints in, we can't estimate them separately anymore because the items are sharing information, right?
Okay.
So it's like, and that configural is literally that way. I mean, that is literally adding things up from each. So cool. So now you already know how to compare these two. How did we compare models before? In R, it was the ANOVA function. Actually, let me just run this model real quick. Run. You can see our estimates. You can see our output right here. And now what you should see, just to double check you're doing it right. By the way, a lesson from my frustration this week, always check that the parameters you think are equal should be equal, and the parameters that you think should be different are different when you look at your output, right? So what we set equal, we set the factor loadings to be equal. Here's the factor loadings for group 1 for female. Let's just take a look at the first one, 1.18. It should be the same as the factor loadings for group 2, 1.18. Okay, hooray. I don't care if you've done this for, 15 years, like me. Always check that what you think are equal, because if you have a typo in your syntax and it mislabels it, maybe you make a 1 an I or something, or the vision or whatever else, or looks very similar, hard to detect, it will go with a different parameter. So
always check that
the things that you believe to be equal in the analysis are actually equal.
L1 to L9.
L1 through L9 should be equal across both groups. The other parameter that we allowed to be free, though, we should check that the variance is set to 1 in the female, the first group, and estimated in the male group. And it is 0.863. And so what this is telling us is the following, that if we anchor the female group to 1 for the variance, the male group's variance is 0.86 the size of the female's variance. It's a little bit smaller, right? But remember, all that's subjective. It's all relative to where that first one is. What do you think would happen to the variance here if I made the variance in the female group 10 instead of 1? It should shift, right? The decimal place should go. If I don't break the model, there's 10 for the variance in the female group right here. And in the male group, it is now 8.6, right? So it's effectively, that's where the anchoring is coming. You're still setting the scale of the factor. It's now all the other group factors are relative to where you put the first one.
And how would you interpret that in a sentence?
In a sentence, the way I like to think about it is, particularly when we have the first group set to 1, it's a proportion or it's a multiple of the first group's variance, right? So if we're talking about this here, it looks like, again, this is sort of what we talk about at the end of the analysis. We're not quite there yet, but just as an initial pass, the variance in depression for men is about 86% the size of the variance for depression for women, right? Because it's relative to that first one. So this number represents relative to the other group. And that's why having that factor variance set to 1 is really helpful, because ultimately, if this is a value less than 1, you can talk about it as a proportion, right? Or if it's a value more than 1, it's not a proportion. It's now this is a multiple of, right? If this variance was 2.5, you'd say the variance in depression in men were 2.5 times the size of the variance of depression for women. Does that seem to But this is the anchoring I'm talking about, the linking between the two, right? And that's why we have to free it itself. Okay. Now, let's test it. You already know how to test it. It's the ANOVA command. And by the way, that is like the best thing about it, LaVon. Because to do this in M+, you have to go and calculate the MLR scaled chi-square statistic first, and then it's a mess.
I have a
Jihan.
question on model comparison. To do the ANOVA function, you have to make sure the two models are nested with each
That's
other.
right.
But for the metric invariance model, the factor variance are free, but the factor loading are constrained to equal.
Oh, right. But because the factor variance is free, effectively what we've done is switch. This is one of these, it's a shell game, right? So we could have allowed the factor variance to be free in the first model and identified the thing differently, right? So we can on the surface it looks like they're not nested because they're going in different ways, but that's only a quirk of us having to identify a scale one way or the other, right? So had we done it that way, had we fixed the configural model to have in group 1 the factor variance 1 and in group 2 the factor variance estimated but a marker item of 1, then now all of a sudden they do become nested because now we have the constraint is no longer the constraint for that first item is not equal to 1. Right, and so that's how we would re-express it. But in trying to teach this, it's a little bit easier to start with everything as a separate analysis itself. But that's a very good question. Thank you for asking it. So, what does this result tell us?
No differences.
No differences. That p-value is large, meaning that our null model, which is the metric model, the one with fewer parameters, fits just as well as our alternative model, the one with more, which is good. That tells us that there's no differences in the factor loadings between the groups. And that tends to be the big one for talking about whether or not the items are on the same scale or measure the same thing. Scale is a little bit different. That's where the scalar comes in. But this is talking about, I think the word metric comes from the measurement. We're measuring when the factor loadings are the same, there's no differential item functioning. People for the same factor have the same value of the predicted value that comes from the factor itself is the same, regardless whether you're a male or a female in this. So if I can actually go back to the slides now. Uh-oh. Thought I could.
So
yes.
it's typically comparing like because we use ANOVA, it's figured out like a mean for one group with the mean for the other and compare if it's significant from the
say that again.
from the grand mean of all.
I'm not following. Say that again.
When we use the ANOVA function to compare the two models, it's compared two means.
They're comparing all of the things that you've constrained. So it's an omnibus test itself. And what we're comparing is whether or not, in the null model, whether or not the factor loadings are equal across groups. So factor loading for group 1 is equal to factor loading for group 2. And so there's a set of however many factor loadings we have minus 1 constraints we're doing.
And like there is an embedded feature that will adjust for the type for alpha.
No, it's an omnibus test. There's just one. It's not doing separate tests altogether. It's one test of multiple.
Yeah.
Like ANOVA, right?
Yeah. I missed it.
No problem. No problem. No, but if it fails, just like ANOVA, now you're in you're right on top of this, right? You're one step ahead actually, because if that p-value is really small, we'd say at least one of those constraints is not correct, and then that becomes the problem, and then becomes the p-value issue. So yeah, absolutely, you're going in the right direction. Yeah, Sheila.
So outside of female and male, so then if it was like a class of students or like a school, and you're looking to see if there's a difference between students with disabilities and without disabilities, what you would want to see is that when you run the ANOVA of your configural and your metric models, that there is not a difference between the two, a significant difference.
That's right. That's right. What you're trying to say, if you want to see that, because ultimately that helps you in your description of what's happening with the analysis itself, with the scale, right? Let me flip forward real quick. The next thing we're getting to is scalar invariance, which is the intercept. But here's a graphic from one of the, I think it's the Brown book. It says this. Here's what's happening, right? If this is the factor on the x-axis, and this is the predicted response on the y-axis, this is what each of the things are saying, right? When there's basically when everything's invariant, when the intercepts and the factor loading is invariant, regardless of a person's factor score, they're going to get the same expected response on the item itself. So effectively, you're doing the same thing. When the item means differ, but the scores, but the factor loadings don't, we have these parallel lines that are going on. And really what that's saying is, what we can say is that the difference that we find here is due to sort of the mean of the item, but once we control for the mean of the item, we're still doing, the factor is still related, the same amount related to that item. And that's the key. When the factor loading is not the same, that's where the problem lies, right? Because you're saying that this item relates differently to the factor in group 1 versus group 2. So effectively, it's like saying, I'm measuring some different construct altogether. Right? If they're the same, it should relate to the item the same across all the groups. And so then the problem, particularly with disabilities or in education, if you think of like when we're measuring math, is 3rd grade math the same as 4th grade math, right? I mean, and the same thing may be true for certain disability groups, particularly if the disability is severe enough where the student has a hard time responding, or there's some other type of rater effect going on, right? It's really hard to disentangle what that means. So
if you'd expect to see a difference based on what you know about the population, then the top left would be problematic because you're not seeing a difference.
Yeah, you wouldn't expect this. That's right.
But then the top right, if you would expect a difference, the top right would be ideal because the means are different, but they're still measuring the same thing.
That's right. It's like saying, for whatever reason, there's a group difference in sort of the average type of response, but but the relationship of the trait to the item is the same, because that slope, remember in regression, the slope is like a proxy for the correlation.
Right. And then C would be problematic because you're not measuring what you think you're measuring.
Not measuring the same thing in each group, right?
Right.
That's exactly it. So you don't, and then the thing is, what are you measuring?
Right.
How do you know? And actually D is a problem too, because you see the relationship is differing as you go along. So then this right here is the case where if you're observing this, if you think about it, if you ignore that, like just let's imagine you didn't test for what we're doing, and if you're going to go and compare, let's imagine this is some type of achievement test, just to make it simple, for me at least. It's the world I've sort of grown up in. If achievement is actually a different thing in each group, if we're comparing students with certain disabilities versus students who are that don't have those disabilities, or different disability categories or different types of disabilities, we're comparing apples to oranges, right? Or if this is achievement testing, and let's talk about some of the biases of testing that we've seen in the past, right? If there's if some of the tests are biased against some type of racial minority, right? We would basically be saying, oh, look, people in that group they don't have the same level of achievement. When really what we're saying is, we can't make that claim at all. We're saying achievement means something different in each group. And I think that's the key. The thing that you have to, with this analysis, what you're trying to establish is when you're saying this group is different than this group on my latent variable, it means you are actually, that's true, rather than it could be that this latent variable is completely different in this group than the other one.
And is a graph like this ever used in publishing?
Occasionally, yeah, occasionally. I think it's a good description of what's happening, right? For what happens. But yet, often we don't see this a whole lot. We see more of this in the IRT world where, again, it's not the linear line, but it's the differences in the curves for each group, right? Yeah. And so, but yeah, that is it. So does that help try to?
Yeah, no, that helps a lot. I think it helps a lot with like knowledge translation. Like these large studies that we try to explain to teachers and they can't understand. I think that is I mean,
absolutely, yeah, absolutely. Well, here's one for you. Here's a fun thing. I know some of you worked on this. Some of you certainly lived it. Those of you who live in different countries, right, this is a great class. We have a ton of different countries represented in this class, right? And it's awesome. I don't ever think. First of all, I don't even think about that normally, but I'm thinking about this is awesome, right? How awesome is it that we have such an international group? Think of all the international comparisons you see, like with PISA or TIMSS, right? Has this been done? Have they checked whether or not the things work? I mean, some of our former students, and I've had the pleasure of sitting on a couple of their master's and PhD committees, and they talk about the basic work of double checking a translation with native speakers. May not even be done in certain cultures, in certain languages, right? Not just language, but also country, depending on different variants of it. So you think about, okay, so now countries are racing. We want to be. I mean, I was really lucky. I gave a workshop in Singapore once, and with the Ministry of Ed, and they're really proud. They're the top of TIMSS in math. Right? They're really proud of that, and rightly so. And they're really concerned about education, and rightly so. That's great. But is it really the case that their scores are 15 points higher, or is it something else about the test that's causing these differences? Right? And so it's an interesting question. And what you're trying to do with this type of analysis is to eliminate the apples to oranges is one of the options as to what's happening. Right? So hope that helps a little bit.
Very cool. I think it helps you account for culture.
Yeah, absolutely. That's it.
Population versus veteran population.
Oh, absolutely. Yeah.
College population versus severe mental illness, like college population.
Absolutely. Or think about like PTSD in different groups. Like is PTSD because of intimate partner violence different than PTSD because you were in a pretty difficult situation abroad in a armed conflict or something like that, right? Definitely. So it is something that sort of helps you investigate things a little bit more because once you put that label on the latent variable, once you call it depression or achievement or PTSD, anxiety, whatever you want to call it, it becomes real, and it's not. And that's the thing. This is trying to sort of remind us that exactly, and do you have to consider it? So cool. I'm glad that I'm able to express this to you a little bit. It's a tough topic. It's so overwhelming the number of steps it takes. And again, this is coming from I live this stuff, right? I'm married to someone who's in statistics in the field. I mean, these are mostly her slides. We do this not just for a living. We do this like this is a hobby too, right? This is like a lifestyle. This is pretty overwhelming, right? So I feel like I'm telling you, like I'm used to being overwhelmed, and this is pretty overwhelming. But I'm glad that I think if I can sort of try to motivate the concept of what's happening, I hope that's good. So let's talk about scalar invariance. Scalar talks about the mean, intercept invariance, if you want to call it that. Do they have the same intercept across groups? And now what we're going to do, everything in this type of analysis sequence builds upon the previous step. So before we saw that we kept the factor loadings the same, and they're going to stay the same here too. But now what we're going to do is we're going to go and lock the item intercepts to be the same. And along with the item intercepts, remember how with the factor loadings, when we put them to be the same, we then freed the factor variance. Guess what we're going to do now? We're going to lock in the item intercepts, and we're going to free the factor mean. And the reason for that is, if we didn't free the factor mean, if the mean was different across groups, it would show up in a systematic change across all the items itself. Right? For the same way that intercept and variance, the variances are yoked across groups this way, and now the intercepts will be too. So if we don't allow that, there's the potential that a systematic difference in group will cause a very big significant difference in the analysis.
And this is an essential analysis which is separate from the previous analysis because you are repeating what you have mentioned many times, that the variance and the mean is...
That's right. They're separate. That's right. They are separate. It's one done separately. So what we'll do is we'll take that exact same syntax we just left with, copy it, paste it in, and now we're going to add to it the item intercepts. Now there's one exception, one caveat that we don't see in this example that we'll see in the next one. Had we found one or more items were non-invariant, meaning they had different factor loadings in the first analysis, it's called partial invariance. But what's customary in the analysis then is to allow, say for instance, if item 2's loadings were separate, then we wouldn't necessarily equate items 2's means. We could in the factor analysis, but we typically don't. Once the item becomes non-invariant, at some point we sort of let the subsequent things be non-invariant for it. So
the residual variances and covariance is always freely estimated across all models.
Right now, we're going to test that next. So we're sort of building on it. Loadings, residual invariance, which is actually accurate. Which I don't know what they'd call that otherwise. It'd be like overwhelming invariance or something. I don't know. So, but you see what I'm doing? I locked all the intercepts down. The next thing I did though is I went and put an NA in the second group, the male group, for the mean, to estimate the mean. I also changed *1 here, which really means the mean itself. That's just one of the arguments for LaVon. If I run this analysis, what's the first thing I check?
Equal.
I check the things I want to be equal are equal, and the things I don't want to be equal aren't equal. So here, we knew the loadings worked before, and I copied that. But let's look at the intercepts now. The first one's 4.24 in the first group, 4.24 in the second group. And then the item mean is 0 in the first group, and the item mean is negative 1.12 in the second group. So that's what we're saying. Okay. So now we can test whether or not we have a significant difference between our two models. And of course, I have another typo. I need to go and redo what's online. And we see now the chi-square is not significant. Well, of course not. This is a book example. This came from Brown. I'm guessing this is simulated data. So things never work this cleanly. We never have exactly 375 in each group, it seems like. I wouldn't say never, but it seems really suspect. All right? So what happens? Here's the thing. Let's pretend this p-value. Normally what we do, if this were our analysis, we just keep moving on to the next step. Good. We're rooting for p-values to be high because that means less work to do. But what happens if this weren't this? What if this p-value is really, really small? What would we have to do? One way to look is to look at the modification indices. Now here's the problem. If we just use the simple modification indices syntax like I've shown you before, it doesn't give you all the modification indices you need to make a decision. Yeah, Sheeta.
So this might be another issue with the online part, but it does say like ANOVA metric estimates and then compared to scalar estimates, but there's an error.
Yeah, that is. No, I just had that error too. I need to go and repair that. So.
When you added one?
Yeah, when I had to add the number 1 here. I'll go update the one online.
Okay.
Yeah. So long story short, I got to leave us here. When you don't have the right p-value, modification indices can help you figure out where the problem lies. But in LaVon, we're starting to get to the limits of what the software can do. It's still beta form and whatnot. You have to add a few things that shouldn't normally need to be there to see all of them. And so when you do that, what you end up getting is a list of everything across groups. So modification index across groups. And then you can restrict only to the ones that you really care about, which for us are the intercepts. And you'd pick out the one that seemed to be the biggest. So for instance here, item 7 has a big one for group 2, and item 7 has a big one for group 1. That sort of tells us item 7 is, it's not, those aren't big. Again, this p-value is very small. They're effectively the same, but just to show you how this would work, we'll start there next time. Okay? All right. I will stop the stream, but if you have questions, you know where to find me after class. I'll be right here. Stop streaming.